Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosine River College in Sacramento, California. In this video, we're going to review how to prove trigonometric identities. This has already been done in one of my previous videos, so this is a part 2. There's really nothing new here other than just new identities that I've written down and a reminder of how things are going to go, because we're about to go into a series of videos where we're going to be solving equations using brand new trig identities. So it's important for us to be able to manipulate trigonometric expressions and to prove identities. As was stated in the previous video, or maybe the part 1 of this video, when you're asked to prove an identity or verify an identity, it's probably best to start with the most complicated side. And by the way, these are rules of thumb, so feel free to break them if you want to. But start with the most complicated side, and then use any known trigonometric identities if you can. Use algebraic manipulations if you can. If all else fails, write things in terms of sine and cosine. And if you get stuck, move to the other side of the equation. The one thing I didn't mention, or actually I did, but I didn't write down last time, do not add, subtract, multiply, or divide between the sides. The moment that you do that, let's say that you want to prove, for example, that it doesn't really matter. Let's say you're trying to prove that sine squared of x is equal to 1 minus cosine squared of x. The moment that you say, let's add cosine squared to both sides, is the moment you're assuming that these sides are equal. You cannot add cosine squared to both sides because we don't know if both sides of this are actually equal. So you need to not cross this barrier. Do not add between sides. Don't multiply both sides by 10. Don't divide both sides by anything. You just have to start on a side and stick with that side. Work on that side until you get stuck or until you arrive at an expression that's equivalent to the other side. So that's the whole trick with proofs, is that you do not assume the two sides are equal to begin with. You have to pick a side and work on it until you get it to look like the other side. In this process, you're going to use all of these identities likely, and I reviewed these in the video right before this, but you need to know your Pythagorean identities, you need to know the even odd identities, the reciprocal identities, and the ratio identities. Every once in a while, a cofunction identity will creep in, not that often though. So just critically important that you keep all of these in your brain. So let's go ahead and start with a verification of an identity. So when somebody says verify the identity, it really means just prove that either the left-hand side is equal to the right-hand side or the right-hand side is equal to the left-hand side. Now, when I look at an expression, or sorry, an equation like this, or an identity like this, and I want to prove it, I will often choose the side that has 2 terms versus the side that has only 1. The right-hand side has 1 term. It's a fraction. It's some junk over some junk. And that is actually harder to pull apart than it is to glue together 2 terms. Let me show you what I mean. So in this proof, I'm going to start on the left-hand side. I'll say the left-hand side. That's what I'm going to do. Is equal to, we have the secant. I'll just rewrite the left-hand side first. So we have the secant of theta minus the cosecant of theta. Well, we know the secant of theta by a ratio identity, reciprocal identity, is 1 over the cosine. We also know the cosecant, again by a reciprocal identity, is 1 over the sine. Now I have 2 fractions, and I'd like to glue them together. So that requires a common denominator, in other words, our algebra. And remember, our ultimate goal is to arrive right there. So we need to eventually get everything glued together as a single fraction. So what I'll do is I'll take this first fraction and I'll multiply both numerator and denominator by the sine. And that's because I want to get a common denominator between these two fractions. In the second fraction, I'm going to multiply both numerator and denominator by the cosine. And this is perfectly legal because cosine over cosine is 1. So you're not really doing anything to the second fraction. And sine over sine is 1. So you're not doing anything to the first fraction other than changing their looks. But once you do that, you get the sine of theta, because now that they have the same denominator, the sine of theta minus the cosine of theta. And this is all over the sine of theta times the cosine of theta. And note, that is exactly where we wanted to end up. That's the right-hand side of our identity that we were supposed to verify. So we started with the left-hand side, and through logical deductive arguments and identities, we arrived at the right-hand side. We have proved that this identity is true. QED, quod erat demonstratum. So it has been demonstrated. And that's fairly typical. In fact, that's somewhat of a low-level identity to prove, but it's fairly typical of the process. Again, carefully reading the directions, verify the identity. We'll pick a side to start on. Well, in this case, we still have on the left-hand side 2 terms to deal with versus the right-hand side, which is a single term. It's just -2 sine cosine. So I'm going to start on the left-hand side because it's the more complicated looking side. And so I'll write left-hand side here. And I'll look for any type of algebra I can do. There's actually 2 pieces of algebra I can do here, but only one of them is going to be helpful. So I'll go ahead and multiply out this binomial right here. So I'll have sine of theta minus cosine of theta squared, which is sine of theta minus cosine of theta times sine of theta minus cosine of theta. So all of our prerequisite algebra skills get used throughout trigonometry. When I distribute, I get sine times sine minus sine times cosine. So that's sine squared of theta minus sine of theta times cosine of theta. And then I'll use blue ink for the other distribution. Negative cosine times sine. So that gives me a negative cosine sine, or in other words, negative sine times cosine. You could write it in either order. And again, distribute this cosine. Negative cosine times a negative cosine is a positive cosine squared of theta. And if you notice, we have a sine squared plus a cosine squared. So I know that is the Pythagorean identity. That becomes 1. And I have 2 of those sine cosines that are subtracting. So you have -2 of those sine of theta, cosine of thetas. And notice I have arrived at the right-hand side of our identity. Oops, no, I have not. Oh, because I missed my minus sign. See what you did? You being me, Roy. So I forgot about this -1 sitting right here. That -1 is sat out there the entire time. Sorry about that. And it cancels this +1 right there. And now we're at -2 sine of theta, cosine of theta. It's good that we keep our eye on the prize, because I would have just said that's the right-hand side and walked on. But now I know it's the right-hand side. Very, very careful there. Sorry about that. So, yeah, keep track of that stuff. QED, that has been proven. That's supposed to be a D. Now, I actually skipped an example here only because once I go over, the other example required the use of Desmos, and once I go over to use Desmos, I lose connectivity. So I'm going to do this one first. So prove that the sine of theta equaling the square root of 1 minus cosine squared is not actually an identity. And we're going to do this by finding a counterexample. So counterexamples are a great way to disprove a statement. If somebody says, I am a super awesome and nice person, It only takes one counterexample to prove them wrong. To say, well, remember that time when you did this terrible thing? See, then you're not such a nice person, or something like that, right? So all you need is one thing that breaks the statement to say, yep, this is not always true. It might sometimes be true, but it's not always true. For example, some people might claim, actually nobody would claim this, I don't think, but let's just pretend somebody claims that A times B is A plus B. Like, oh, if you have two numbers and you multiply them, it's the same as adding them. Well, there are cases where that's actually true. 2 times 2 is actually the same as 2 plus 2. So there's a case where it's true. But to showcase that it's not always true, I just need to find one example where it doesn't work. And 1 times 5 is definitely not the same as 1 plus 5. So there you go. I have provided a counter example. So whomever creates this statement has been proven wrong. That statement is not always true. So that's how a counter example works. You just want to find some place where it doesn't work. Well, this is very close to being an actual trig identity, to be honest with you. And the reason why I say it's very close is because we know that sine squared of theta plus cosine squared of theta, we know that's 1. That's the Pythagorean identity. And so if I were to subtract cosine squared of theta from both sides, well, that would imply that sine squared of theta is equal to 1 minus the cosine squared of theta. And if I were to take the square root of both sides, I would get that the sine of theta is equal to not the square root of theta, or of that right-hand side, but it would equal the plus or minus square root of 1 minus cosine squared. So this statement, while I haven't proven it's not an identity yet, I'm just showcasing it's definitely not true, because the sine of theta is going to be either plus or minus that. So the way I'm going to prove or showcase that this is not always true is to find an angle where the sine is negative. Because square roots, this guy right here, will never return negative numbers. So we're going to let theta equal. Well, let's think about a place where the sine is negative. Well, if you remember, all students take calculus. So I know sine is negative in quadrants 3 and 4 because only the tangent and the cosine are positive. Tangent's positive in quadrant 3 and cosine's positive in quadrant 4. So I'm going to go ahead and select an angle in quadrant, let's say 3. So I'll do 5 pi over 4 because that's just a fine angle to choose. Okay? So we're going to go ahead and say let theta equal 5 pi over 4. Well, sine of 5 pi over 4 is equal to, well, sine of the reference angle, pi over 4. But you have to consider the quadrant where 5 pi over 4 terminates, and it terminates in quadrant 3. So I know it's going to be the negative sine of pi over 4, which is a negative 1 over the square root of 2. On the other hand, the square root of 1 minus the cosine squared of 5 pi over 4 can't equal that, but let's go ahead and mechanically go through this. That's going to be the square root of 1 minus the cosine. Let me write it this way. Something squared. It was originally the cosine of 5 pi over 4, but I'm going to trade that out for the cosine of its reference angle. But remember, 5 pi over 4 is in quadrant 3, and the cosine is negative in quadrant 3. The negative is actually going to disappear because we're going to square it in a moment here. So that's the square root of 1 minus, and then you square that negative, and it becomes a positive. So 1 minus a positive cosine squared of pi over 4. But cosine of pi over 4 is 1 over root 2. So that's 1 minus 1 over root 2 being squared. So that's 1 minus 1/2, or the square root of 1/2 is what it'll be, which is 1 over root 2. Now, is that the same as negative 1 over root 2? And the answer to that is no. So since the sine of 5 pi over 4 is not equal to the square root of 1 minus the cosine squared of 5 pi over 4, we know this statement is not always true. Therefore, it's not an identity. It sometimes actually is true, but it's not always true. And that's why it's not an identity. Identities are always true. So here we have shown this is sometimes not true. Now I rewind back and we're looking at the previous example, which I never showed you. This example says use Desmos to determine if the statement might be true. The reason why I emphasize might be is that using a graph, it never shows that something is true. It demonstrates that it could possibly be true, but doesn't actually show that it is true. So if it looks like the statement is true via the graphs, then we're going to come back here and prove that this statement actually is true. The first thing I want to draw your attention to is if you're going to use Desmos, it does not like that exponent notation. So what I'm going to do here is I'm going to graph the left-hand side of the identity, which is actually the cotangent of, technically it was t, but we're going to raise that to the fourth. So now you see it's actually working, minus, again, the quantity of tangent of x. Again, it was a t, but I'm just writing as an x here, to the fourth. So that was the left-hand side of our identity. And we want to showcase or want to see if that's the same as the right-hand side. So I'll graph the right-hand side. And the right-hand side was a fraction where the numerator was the sine of x being squared and then plus 1. And the denominator was the cosine of x being squared. Now you can see just based upon the fact that the blue curve and the red curve are not identical, that this is not an identity. These two things are definitely not the same. Every once in a while they are, it's true. There's the same at these points right here, but they're not always the same. So this is a really good example of how you can use Desmos to disprove that something is an identity. So somebody might come in and say, I swear these two are the same. You can say, well, look at their graphs. If their graphs look identical, they might be the same. I'd have to prove it. But if their graphs are totally not identical, if it's obvious like this, where you have the first graph right here and the second graph looks like that, where they're not identical, you know that these are not the same functions. These are not, they're not equal to each other. It's not an identity. Therefore, this statement is definitely not true. So not an identity. And that's all I need to say there. So that's a very nice example of, sorry about bad handwriting. That's a very nice example of how to give a counterexample or how to show that a claim is not true.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.